Okay, so let's take care of section 1.5 pretty quickly here. I'm just going to highlight some things, some vocabulary in this first little part. So you have something called a homogeneous or homogeneous, I say homogeneous, linear systems. So a homogeneous linear system, it's a linear system of equations is called that if you can write it in the form ax equals 0. So that means that basically the answer column is 0 right here, right? And so that's called a homogeneous system of equations or a homogeneous system of equations, okay? And so, or if, if it's not originally like that, maybe you could do some operation to try to get it like that. All right. So for this kind of system of equations, there's always one solution, and that solution would be 0, the 0 vector, if you, or 0, 0, 0, like however big your system of equations was. Because think about it like this. Like if you had like this equation right here, like you could always put 0 here and 0 here for x1 and x2, and you would get 0, because 0 times something plus 0 times another thing would equal 0, and you could put it here and get 0. And so that's called the trivial solution. So that's going to be a word that you hear pretty often, the trivial solution. That always exists if you have a homogeneous system of equations. Okay, so it should be kind of logical, right? So the important question is whether or not there is a non-trivial solution, because we always know that we could plug zeros in and get 0 back, all right? And so we want basically a non-zero vector that satisfies the equation ax equals 0, okay? So this is only going to happen if you have a free variable. So let's go ahead and see what happens here in this one. So if you do some row operations, you notice, and also in a way, you don't have to put your augmentation on the side, because no row operations are going to change this 0, 0 right here. So if you do some operations to 1 and 10, like multiply, the first row by -2 and add it to the second row, obviously you get this right here, and you can imagine that the zeros are there as well if you would like. Okay, and so you notice you have a free variable, right? x2 would have to be free. And so looking at example 1, remember free variable means infinite solutions. Does this system have a non-trivial solution? So it always has a trivial solution. You can always put zeros in for x1, x2, x3 and get 0, and same thing in this bottom one, right? But does it have a non-trivial solution? So let's go ahead and look at it. So if you ref this in your calculator, I figured we've done enough of that lately, so we can just skip right to it. And if we do that here, this is what we get. Remember, this is our augmented matrix right there. So look at that. We have x3 is free, right? Okay. So when we go to write our answers, we got x1, x2, and x3. x3 is equal to x3. That's how you write that. x2, this column here, there would be positive 5 x3. And this guy here, x1, would be positive 6 x3. Right? Because if I had to write that originally, remember it would be, this guy here would be x1, 1x1 minus 6x3 equals 0. That was this equation, what it turned into. The bottom one turned into x2, 1x2 minus 5x3 equals 0. And so basically we've just solved for x1 and x2 and x3. So if we wanted to write this as a vector, remember we would write it like this. We would take 6, 5, and 1, because those are the coefficients of x3. And actually you would go ahead and put like a little x1, x2, x3 in the front also. So x1, x2, x3, and you would say it equals that. That would be the vector way of writing this solution. So whatever the book asks for is fine. All right. So the next little part right here, the following are in parametric vector form. That's kind of like similar to what we have. So if you have a combination of vectors that lead to your answer, like you've seen before, like we did our little whiteboard stuff in class last time, or in class today, this is just kind of an example of that. All right. So solutions of non-homogeneous systems. When a non-homogeneous linear system, so that means it doesn't have all zeros at the end. has many solutions. The general solutions can be written in parametric vector form as one vector plus an arbitrary linear combinations of vectors, like I showed you earlier. All right, so we're going to do that right down here. So actually, this is like super similar to this last one, but this is actually in this example is homogeneous, but whichever, you can do both. All right, so we see that x3 is free right there. So we're going to have 1, 2, 3, so x1, x2, and x3. And if you can jump right to this format, it would be a little bit easier, but sometimes you might want to do this. X1 is -4 x3. x2 is +3 x3. And x3 is just itself. So everything involves x3. And the coefficients are -4, 3, and 1. Okay. So a lot of times, I don't know, personally, I kind of have to write it out like this most of the time first. All right, so now the next one, we just have a little more complicated situation. So this is already in row echelon form. We have the ones right here. And so describe all solutions of ax equals 0 in parametric vector form where a is row equivalent to this. So remember, row equivalent just means that this is the reduction. This is one of the reductions of the original matrix A. And so you can put the zeros on here to imagine, because I did tell you this information there. So there are zeros on the other side. So I like to do that just to, help myself out. All right, so if I write this out, x1 is going to be 2 x2 plus 9 x3 minus 5 x4. So I got 1, 2, 3, 4. All right, and then I have x2 is going to be -2 x3 plus 6 x4. Now, x3 and x4 are both free, so they're equal to whatever you pick them to be. All right, so this way you can see what you have. So I have, if I want to write my answers, I need 3 vectors to write them. I need a vector for x2, a vector for x3, and a vector for x4. If I look down here. Now, not all of them have that, but let's go ahead and do it. I do not need a coefficient vector because my system was homogeneous. All right, so let's do a vector for x2. So if I see all the coefficients of x2, I got a 2, and I have no x2s anywhere else. So I have a 2, and then 0, 0, 0. All right, so then a vector for x3. So I have 9, -2, 1, and nothing. 9, -2, 1, and nothing. All right, and then a vector for x4. All right, so then x4, I got -5, 6, nothing, and 1. Okay, so that's what this section is about, and or this, this what that example is just trying to get you to do, to write something in vector form. So it's just a little bit of a pain, but that's how it is. All right, so there is something, parametric equation of a line through A parallel to B. So this is kind of similar. Remember back in calculus when we used to make you write parametric equations of lines, right? Like let's say we had the direction vector. And our direction vector for our 3D line was like 2, 5, -3. And let's say we had a point. And the point that this line went through was like 4, 0, 7. Remember, we used to do this. X equals 2t plus 4. We did y equals 5t, because that was my direction, and then plus nothing. All right, and then z equals, I would say, -3t plus 7. So this is just going to be that. If I was going to write this in like parametric format, I would write, I would separate these vectors 2, 5, -3, and 4, 0, 7, and so into pieces. And so if I was going to write the equation of this line in parametric form through A, so A is my direction, oh sorry, A is my point, and B is my direction, I would write this. I would write x equals, let's see, direction, so -7, 8. Put your t with that. plus 3, negative 4. That's how you write a parametric equation of a line. I think, if I remember right, the definition of that is in the book, but this is a real simple thing. All right, so just a recap here. Writing a solution set in parametric vector form, you're going to row reduce everything. You're going to express each variable in terms of all the other variables that they need and free variables. And you're going to write the solution, and then you're going to separate things out into vectors. So we're just going to do that just here. So this is kind of a large one. Remember, this right here represents an augmented matrix. So this one right here, this is my augmentation right there. And it's going to have a coefficient or a constant column as well. So let's go ahead and write it the normal way. So x1 right here would equal, so remember x1, x2, 3. All right, here we go. So I got negative 2, I'll move that over. So negative 2x2 plus 3, x4, and plus x6, no number. x2, oh, x2 is free, so x2 is x2. Let's see, x3. So remember, my free variables are things without pivots. So x2 is free, x4 is free, and x6 is free. So x2, x4, x6. All right, so let's worry about x3. So let's go to x3. He is negative 2x6 plus 1. Let's worry about x5. He is negative x6 plus 2. All right, so we need a pretty big space here. I got x1, x2, x3, x4, and 5, and 6. This is my vector solution. All right, so look at my answers. The first thing that it involves is x2, so I'm going to make a vector for x2. I got negative 2 and 1. I have nothing here, nothing else has x2's in it. All right, my next vector involved is x4, right? Okay, so I need a vector for x4. All right, so I got 3, nothing, 1, nothing. So 3, nothing, 1, nothing. All right, my next one involved, I don't have a 5, so let's say 6. All right, so 1, nothing, negative 2. All right, and then let's see, 1, nothing, negative 2, nothing, negative 1, and 1. And then finally, my coefficients, or my constants, sorry. I have no constants, then a 1. So 0, 0, 1. Then I have no constant, I have a 2, and I have no constant. So that is written in vector form, my solution. And that is it. Bye-bye.